Good day everyone, and welcome to our presentation. Today, we delve into the fascinating world of artificial intelligence with our paper, Neuromorphic Dreaming, a pathway to efficient learning in artificial agents. We explore how we can make AI more energy efficient and biologically plausible, drawing inspiration from the remarkable learning capabilities of biological systems. Join us as we unravel our innovative approach to model-based reinforcement learning using spiking neural networks on neuromorphic hardware. Let's embark on this journey to create intelligent agents that learn efficiently and adapt effectively in real-world environments. Stay tuned. In the realm of artificial intelligence, we often marvel at the power of advanced models, but overlook a critical aspect: energy efficiency. Biological systems, in contrast, demonstrate the ability to learn complex skills quickly and efficiently, often with limited data. This highlights the need for more biologically plausible models in AI. Deep reinforcement learning algorithms, such as Deep Q network and twin-delayed deep deterministic policy gradient, have been adapted for spiking networks, showing promise in handling complex control problems. However, these adaptations face challenges, including the efficient utilization of limited online data and limitations in managing complex control scenarios. To address these issues, we propose a model-based reinforcement learning approach that uses spiking neural networks. This approach is compatible with neuromorphic hardware and has been demonstrated to be more sample efficient than current reinforcement learning methods. This paves the way for creating intelligent agents that can learn and adapt in real-world environments with limited data and power consumption. The rapid advancements in artificial intelligence, particularly in the realm of neural networks, have been nothing short of remarkable. However, amidst this progress, one critical aspect often gets overlooked: energy efficiency. The digital chips that power these immense neural networks are not always the most energy efficient. Our goal is to bridge this gap by developing models that are not only biologically plausible, but also energy efficient. The figure you see here illustrates the structure of the agent and model networks used in our study. The input to hidden connections are fixed and randomly initialized, while the learnable hidden to output connections are trained using a policy gradient method. This setup allows the model network to predict the next state and reward based on the current state and action inputs. In essence, we are striving to create a balance between the power of AI and the need for energy efficiency, taking inspiration from the remarkable capabilities of biological systems. Deep reinforcement learning, or DRL, and spiking networks have been making waves in the field of artificial intelligence. Algorithms such as DQN and TD3 have been adapted for these networks, showcasing their potential in handling complex control problems. However, we face significant challenges with existing methods. Most training algorithms rely on non-local learning rules, which are not only computationally intensive, but also biologically implausible. These methods also struggle in complex control scenarios, and efficiently utilizing limited online data remains a significant hurdle. In the face of these challenges, we must strive to develop more efficient and biologically plausible models. This will pave the way for more advanced and energy-efficient learning systems. The EPROP method, a biologically plausible form of actor-critic and backpropagation, has shown promising results, achieving performances comparable to non-spiking systems in benchmarks like Atari games. However, we propose a different approach using model-based reinforcement learning, or MBRL, which employs spiking neural networks and is compatible with neuromorphic hardware. This approach has been demonstrated to be more sample efficient than state-of-the-art model-free RL approaches. Now, let's talk about the neuromorphic processor architecture we're using, the DYNAPSE. This architecture implements essential neuronal dynamics with the XLIF model. It operates in the subthreshold domain, which is a design choice aimed at minimizing dynamic power consumption. This is a crucial aspect of our work, as it allows us to develop more energy-efficient models. In our research, we've made significant strides in the realm of artificial intelligence and neuromorphic hardware. We've successfully implemented a model-based reinforcement learning approach using spiking neural networks in real time on neuromorphic hardware. This is a major achievement, as it combines the sample efficiency of the MBRL approach with the energy efficiency of neuromorphic hardware. But we didn't stop there. We put our approach to the test using the classic Atari Pong benchmark. The results were impressive, demonstrating state-of-the-art performance. This validation shows that our approach is not only theoretically sound, but also practically effective. It's a promising step towards creating more energy-efficient and biologically plausible AI models. Our research proposes a novel approach to reinforcement learning, leveraging the power of spiking neural networks. This model-based reinforcement learning method, or MBRL, demonstrates superior efficiency in terms of data usage compared to existing model-free RL approaches. This is a significant advantage, as it allows for effective learning with limited interactions with the environment. Furthermore, our approach is compatible with neuromorphic hardware, a type of specialized hardware designed to emulate the computational principles of biological neural networks. This compatibility offers several advantages, including the potential for low power and scalable implementations. In essence, we're developing intelligent systems that can learn and adapt efficiently, drawing inspiration from the way biological systems operate. Our research leverages the DYNAPSE neuromorphic processor architecture, which is designed to emulate the computational principles of biological neural networks. This architecture implements the exponential leaky integrate and fire model, a biologically realistic neuron model. To ensure energy efficiency, the system operates in the subthreshold domain, minimizing power consumption while maintaining computational functionality. Now, let's delve into our proposed research. We aim to implement a model-based reinforcement learning approach using spiking neural networks on this neuromorphic hardware, and we aim to do this in real time. This approach is not only compatible with the energy-efficient neuromorphic hardware, but it also demonstrates superior sample efficiency compared to traditional model-free reinforcement learning methods. To validate our approach, we tested it on the Atari Pong benchmark, a classic testbed for reinforcement learning algorithms. The results were promising, with our system achieving state-of-the-art performance. This shows the potential of our approach to handle complex control problems while being energy efficient. Our research introduces a novel training approach for the world model. This model employs a feed-forward spiking network, which consists of an input layer, a hidden layer of silicon neurons, and a readout layer. The input layer encodes the current state variables and the selected action. Interestingly, the input to hidden synaptic connections remain fixed during learning, focusing the training on the readout weights. These weights are updated using EPROP learning rules, a biologically plausible method. This approach sets our work apart from previous studies in several ways. Firstly, we use local learning rules, which not only offer biological plausibility, but also enhance computational efficiency. Secondly, our method proves to be more sample efficient than existing model-free reinforcement learning approaches. Lastly, our approach is compatible with neuromorphic hardware, offering significant energy efficiency advantages. This compatibility allows us to implement our model on energy-efficient devices, making it a promising solution for real-world applications. Our research was put to the test in the dynamic environment of the Atari Pong video game. We focused on measuring the sample efficiency of our approach, which is the average return achieved per game. To understand how the agent's decision-making evolves, we tracked the entropy of its policy throughout the training process. Each training run was comprehensive, consisting of 2,000 games, with each game lasting 100 frames. This rigorous setup allowed us to thoroughly assess the agent's learning progress and ensure the robustness of our findings. Our research has yielded some key results. We've successfully implemented a model-based reinforcement learning approach using spiking neural networks on neuromorphic hardware in real time. This was validated on the Atari Pong benchmark, where we demonstrated state-of-the-art performance. Importantly, our approach achieved sample-efficient learning, requiring limited interactions with the environment. This underscores the potential of our method in creating energy-efficient learning systems. Furthermore, our work highlights the potential of biological neural networks and neuromorphic chips in developing intelligent agents that can learn and adapt in real-world environments with limited data and power consumption. Looking at the graph, we can see the average return per game over the last 50 games as a function of the number of games played. It's clear that the agent using the dreaming phase significantly increases its average return in terms of interactions with the real environment. The graph also shows the evolution of the policy entropy during training, which quantifies the uncertainty in action selection at each game. As learning progresses, the agent's confidence grows, indicated by a decrease in entropy. Now, let's revisit the key contributions of our work. Firstly, we've successfully implemented a model-based reinforcement learning approach using spiking neural networks on neuromorphic hardware in real time. Secondly, we've validated our approach by achieving state-of-the-art performance on the Atari Pong benchmark. This was accomplished through sample-efficient learning with limited environmental interactions, demonstrating the potential of our approach. Our research has demonstrated the potential of model-based reinforcement learning with spiking networks on neuromorphic hardware. This approach allows us to create learning systems that are both sample-efficient and energy-efficient. By leveraging the computational advantages of neuromorphic chips, we can develop intelligent agents that learn and adapt in real-world environments, even with limited data and power consumption. As we look to the future, the introduction of next-generation neuromorphic chips could enable us to tackle even more complex tasks. In terms of future directions, we believe that continued research in this area can lead to significant advances in neuromorphic computing. This could have far-reaching implications for fields such as robotics and autonomous systems. The introduction of next-generation neuromorphic chips will further enhance our ability to tackle complex tasks, opening up new possibilities for the application of this technology.